This is Lab 2 for Klaus Mueller's computer visualization class. For this lab, I chose to continue on my Lab 1 dataset, which consisted of top Spotify songs and their attributes. This main page of Lab 2 is a scree plot that visualizes the PCA decomposition of the dataset. Using the scikit-learn PCA decomposition feature, I broke down the dataset into 15 components, one for each key attribute. Each bar in this graph represents how much of the variance overall is explained by each component, ordered descending. So this first component represents about 22% of the variance in the graph, or in the dataset. The second bar represents about 18%. This line is a cumulative count of the bar values. So you can see bars 1 and 2 jointly represent about 40% of the variance in the graph. This is our descending, and as you can see, the cumulative count approaches 1. If you would like to view a scatter matrix, you can select a dimensionality index by choosing a bar. So if you want to select a dimensionality index of 2, you click this bar at 2, and then it shows 4 attributes in the scatter matrix. These 4 attributes are chosen based on the 4 attributes with the highest sum square loading based on the 2 components that were the top 2 components from the PCA analysis. If you would like to see a graph including the loadings of the top 2 PCA dimensions and the 4 attributes in question, you hover over the legend, and you can also view the sum square loading at the bottom. The attributes that were chosen because they had the highest SSL value based on the two dimensions, with the number of dimensions being decided by the dimensionality index. To read this, you look at the attribute on the same row to represent the y-axis label, and the attribute in the same column to represent the x-axis label. So for this graph, the x-axis label is popularity and the y-axis label is acousticness. The transpose of the graph is found here. So in this case, the acousticness is the x-axis label and the popularity is the y-axis label. You can see the dots are simply flipped across the y equals x line. For this graph, the y-axis label is acousticness, and the x-axis label is valence. Now, you note that for this, the dimensionality index is 2, and the 4 attributes are acousticness, popularity, energy, and valence. However, if we return to the original scree plot, we can change the dimensionality index to say 8, and popularity, acousticness, position, and valence are the 4 attributes. Pardon me, but I don't quite remember if this is the same as earlier. But yeah, if you choose a dimensionality index of 1, you can see the 4 are now acousticness, energy, valence, and position. So you have energy, and energy is the attribute that changed based on the number of dimensions that were selected. And in this case, you can see only 1 dimension and the 4 attributes. Now, ideally, you could perform an elbow test to choose the optimal number of components that we care about. It's a bit difficult because it decreases rather linearly, but I believe that 4 might be a good value to choose. So you can see the 4 dimensions, and you can also in the legend change the number of clusters. So you can see it's colored green and blue based on, by default, with 2 clusters, but you can change it to 3 and add the violet, and you can change it to up to 9. But in this case it gets very messy and the clusters are not necessarily as helpful. I think 3 has shown itself to be a good value because you can see like clear separation and at least a few of these graphs. Now, if you want to turn to the scree plot, and that's the scree plot in the scatter matrix, you can also view a PCA biplot. Now this PCA biplot graphs not just the points according to the most influential two components, but it also shows the unit vectors for each attribute. So in this case, each of these lines represents the 15 key attributes selected, and they are graphed against the two PCA components with the highest value for the explained variance. They are obtained by performing the inner product of the unit vector for each dimension, each of the 15 dimensions against the two components from PCA. You can also change clusters here as well to review all the different clusters, although it's very tightly packed, so it might not be the most interesting. You can also view the MDS plot. So this is multidimensional scaling. We perform multidimensional scaling using the scikit-learn feature as well. In this case, the distance between the points represents the pairwise distance between the vectors in 15-dimensional space. MDS simply simplifies it to 2 dimensions, and that way you can graph it. So these 2 points are very similar to each other in 15D space, while this and this are very distant from each other in 15-dimensional space. This looks very different from the scree and the biplot because for the MDS and the PCP plots, I intentionally used the unscaled data. However, for the first two, I used the scaled data because that yielded more interesting results. Otherwise, the two PCA dimensions dominated the explained variance. So in this case, you can see the graph shape is very tightly clustered here with a very strong line. And because of a misreading, I ended up accidentally implementing an extra feature, which is you can view it in both Euclidean and Manhattan distance. So when you switch to Manhattan distance, the shape changes radically, and you can see there's a lot more distance between points. Switch between the two. But more interesting is the correlation. This was plotted using a correlation. This was the MDS of the correlation matrix of the 15 attributes among each other. So 2 very correlated attributes will be graphed very closely to each other here. You can see a tight cluster here. That's the reason I chose to do show label on hover rather than show label by default. It's because if I had the labels on for all of the points in this region, it'd be very difficult to read and distinguish between the points in the text. So I chose to do label on hover instead. Now you can go to the parallel coordinate matrix using this drop-down, but then that has a default ordering. If you want to customize the initial ordering, you can simply click on the points from the MDS plot in order. So maybe we could start with these points. And once you have all 15 points selected, a View PCP button comes up, which will move you to the PCP plot where the axes are ordered in this ordering. You can also clear the selection if you want. But yeah, if you go to the PCP plot, you can see it's in the same order: position, streams, and then the rest of the attributes are in that one big clustered region. So the PCP plot is very useful. You can look at correlations as well based on the trends and the rises and falls and where the line density is the greatest, while also looking at multiple dimensions. You don't have to look at it graphed specifically to 2 PCA dimensions or for the MDS simplification. So you can see that you have a variety of positions, and that the lower positions or the higher positions, which indicates it has the songs that appear in the higher positions, so further away from one, have fewer streams, whereas the songs that appear in, like near the number 1 spot have greater amount of streams. And in this case, you can look for trends. Yeah, so the obvious one is positions is inversely correlated with streams, but you can also notice that there's a fair amount of there's not many. I believe there's only 3 discrete time signature values, just because a few time signatures are very common in music. Tempo, duration. You see there's a wide variety of acousticness and instrumentalness, but then there's not much variety in speechiness. You can see songs with more energy also tend to be louder, have higher valence, have higher tempo, which makes sense as well. And if you want to reorder them, other than using the MDS way of ordering the axes, you can also individually do it using the swap buttons at the bottom. So you can see position is the first axis and streams is the second, but if you flip them, streams is the first and position is the second, and maybe that can help you draw a more interesting picture. Maybe this makes the inverse correlation between streams and position more clear. So let's say another feature of this is that you can do filters. So for example, if you look at acousticness, you can see that one of the big methods for the clustering, or one of the best ways to explain the 2 clusters here, is acousticness. Most of the blues are less acoustic and the greens are more acoustic. So you can create filters by clicking and dragging. When you hover over an axis, it turns to a cursor. Once you see the cursor, you can click down and drag. I apologize. You could click down and drag, and then you can filter out only the points that have these specific values for acousticness between roughly 0.45 and 1. And you can see the patterns for the blue cluster. You can see this blue cluster tends to be more acoustic, middle range for loudness. They have a more even distribution through the year, but if you want to remove it and then specifically focus on the greens, do that as well. And the green ones are clustered at the end of the year, or they're far more recent, and you can look for patterns that way. You can create multiple brush filters as well. No green. And you want to look at the greens, and you also only want to look at the greens that are shorter, like less than 2,000 or 250,000 milliseconds. So you can slowly filter out the lines to create more to look at specific subsets of data points, and simply click on them to delete the filters. The filters stay in place if you swap, so you don't have to worry about that. And play around with the number of clusters, and this is a visualization that you can play around with and potentially look for patterns with. Yeah, those are all the points, as well as the extra credit with the MDS ordering. So that's everything. And again, the data source is visible here. And this top right drop down, if you would like to visit this page directly and without having to run the Flask app yourself, you can simply use this URL at the top just to access the web hosting version. Thank you.